Okay, so I'm going to go through the lecture material you probably have seen already. And tomorrow, hopefully, we'll start diving into deep learning. Okay, so we're going to see feed-forward neural nets tomorrow. Okay, so we've seen a number of classifiers. Okay, so this is just a reminder of what we had. So this is your testing set and training set as well. So you have two classes, and the green and the orange, and you want to separate both classes. And what you see in this this maps is the decision boundaries. And so you have the probability to belong to one class. And so green is belong to class green, and orange you belong to the class orange. And you've seen that for here's 5 different types of algorithms we briefly looked at. Okay. So it's all good, and as usual, when you start with a problem, you might try a whole bunch of those classifiers. But then the question you have, of course, is how you compare those classifiers. And so we're going to start with the binary classifiers, okay? And to understand what's going on with binary classifiers, we're first going to look at what's going on really, okay? So we'll come back to the problem of the loss function later on, but we'll start with here the confusion matrix. So in the confusion matrix, all what we're doing is we're having a table that compares what we predicted against what was the actual class. So it's quite simple. So we have this is actual 0. So we actually the observation the class of the observation is class 0, and this would be actual 1. So the prediction is the actual class is 1. And here you have the predictions. So you predict 0 and you predict 1. Now the order in which these entries are, it doesn't really matter, okay? And the point, you have a table that explains that, and then the entries here are simply the number of observations which fits into a particular case. So let's say maybe we have 80 observations for which the prediction was 0, and in fact the class was 0, and then maybe we had say 15 here for actual and predict, and maybe, I don't know, 33 and 10, okay? That's probably a very poor one, so let's make it 45, okay? Okay, so this is how it presents, and I stress here that the number you see here is the actual number. It's not a ratio, it's not a percentage, it's just the actual number here, at least in this formulation. And so you have two classes, okay? So two situations. So situation 1, you're correct, okay? So this is these two versions here. So on the diagonal, you're doing a good job, and off the diagonal, you're doing a bad job, okay? In fact, any cell that is not on the diagonal is just bad. And so you have different names for each of these entries. So this one, so you have, remember, like there's different names for the classes. So usually 0, you can say it's false, okay? Or you could say it's negative. And 1 usually would be true or positive. Okay, so when you talk about binary classifier, I might use the word negative or positive, and negative just means 0, and positive means 1. Okay? So with this in mind, so we have, so let's look at the one that works. So if you predict 1 and you have 1, it's called a true positive. Positive. All right? True positive. If you have 0 and you predict 0, then it's called a true negative. Okay, so true because you're correct, and then you just say the class. Okay, and then you have 2 errors. So you predict 1 and you actually have 0. So that's a false positive. Okay, so you predict positive, but actually it's not true, it's false. And here, of course, would be false negative. Okay, so that's 4 types of outputs you can have. And the point I want to make here is it's very important that this. Okay? So you have actually 2 types of errors. So it's not just like you make an error in the prediction. Okay, you have 2 types of error. One is called the false positive, and the other one is false negative. And that really is the key here, is that when you compare classifiers, you can't just use one metric. Okay, so there's no way around that. You cannot find a single number that would say how good your classifier is. Okay, you always need 2 numbers, and the reason is because actually you have 2 types of data, 2 types of error. Okay, so it's one of these problems you have to buy a washing machine or a TV, and there is 2 criteria that are important. So say TV, the size of the TV, and I don't know the number of pixels you have. Okay, and for you these 2 are very important, and there's no way you can just merge those into a single number. They're just it's 2 criteria that you need to fulfill. Okay, so here's the same. You have 2 errors, and there's no way around that. You always need 2 numbers, 2 metrics to be able to go around that. Okay, so these false negative and false positives, they have a name, and this is what happens. So in the medical world, okay, so on stats, so false positive is referred to a type 1 error, and the false negative is referred to a type 2 error. Okay, and I hope that will help you remember which one is which. Okay. Now all these names are quite confusing, and you'll get, when you read the slides, you'll be like, okay, that makes sense, and then you get confused after a while between all these names. Okay. But try to remember the most important ones. Okay, at least true positive, false positives, and a few of the metrics I will mention. They are quite important, and if you read papers, that's the kind of metrics people will use. So you kind of have to know them by heart. Okay. All right. So why is it so important to have 2 metrics? So I said we have 2 metrics because you have 2 types of error, and one of the aspects of why it's so important is because you can fool. You can fool the metrics, okay? So before I explain that, I'm just going to show you, present briefly, the types of error you will see in the literature, okay? So the first one is a recall, okay? So the recall has different names, okay? So it's called the true positive rate, and basically. It's a proportion, okay? So it's a proportion of, so the P here corresponds to all the positives, okay? So that's all the positives you actually have in the actual positives you have in your test sets, okay? And this is, if you're on the proportion of true positives you retrieve from your test sets. Okay, so if you're doing a search engine, okay, so you have a number of pages that are relevant. So there'll be all the positives, okay, so all the class 1. So these are the pages you want to retrieve. And the recall will be the percentage of correct, relevant pages you retrieve. Okay, so it's the ratio, the percentage of the class 1 you identify as being class 1. Okay, so then you have precision, which is another very popular metric, which tells you something different, okay? It's what tells you how precise you are about your query, okay? So in the recall, it's very easy to have 100% recall, okay? If you just have a system that returns 1 all the time, okay? So if your prediction is y is 1, so you just return 1 regardless of what the input is, okay? So it's a very poor system, okay? So you have a internet search engine that only returns 1 link, okay? Then you can still have extremely good recall because you can have 100% recall. No, sorry, my mistake. Okay, well, we'll see that later. We'll see that later. Sorry, I'll come back to that later. Okay, but the point is, you can have very good recall while still doing something very bad. Sorry about that. I'll come back to that later. Then we have precision. Okay, so precision is kind of like what's the probability that you made the correct guess. Okay, so you predicted it's going to be 1, but what's the probability that indeed it's going to be 1? Okay. So you know your system says I predict it's class 1, but how much confidence do you have in that prediction? Okay, so you can measure that. You can do statistics. You collect all the ones that are indeed true, and divide by the number of ones the system returns. So the number of ones that you return is all the true positive and the false positives. Okay, so all the positive, regardless they're true or false. All right, and you take the ratio of that. Another one here is the false positive rate. Okay, so same as recall, kind of, but for negative numbers. So it's a ratio. It's a proportion of. It's a proportion of negative numbers that are incorrectly labeled as positive. Okay. So you're going to look at all the negative numbers you're supposed to have, and you look at how many are actually flagged as being positive when they should have been negative. So it's kind of the error you have. So you want the false positive rate to be very low, obviously. Okay, so you want to make as many possible false positive predictions. Okay, so here you're looking at the number of times you're making an error by saying it's a positive when it's not. And then you have these two other guys, accuracy and F1 score. So accuracy would be the kind of the one you would think first of, okay? So that you combine all the types of error you make, and so in this case, and regardless of whether they're positive or negatives. So, so the accuracy is defined as being the ratio of your true positive plus true negative divided by the sum of all your elements. Okay, so p plus n, that would be the number of observations you have in total. So you're looking at the number of times you're correct, so true positive plus negative, divided by the number of observations you have. Okay, so what percentage of your predictions are actually correct or not? Okay, so 1 minus this number would be the number of times you're incorrect. Okay. And then you have the F1 score, which is kind of a weird one, but basically you're trying to combine the precision and the recall into a single number, which is called the F1 number. All right. So the F1 number is kind of an attempt at creating a single metric that captures two metrics at once. Okay, so you're trying to say, right, I can combine the recall and the precision into one metric. So it's kind of harder to fool. Like the F1 is used as a shorthand. If you have to use one metric to compare algorithms, if you don't have a choice, you just want to use one metric, you would go maybe for the F1 number, okay? Because it's harder to fool, okay? But the other ones, but anyway, you still need two, okay? And the F1 is just a shortcuts. Okay, so these are 5 ones. Just look back at those and just know that they exist, okay? Right, so here's what I want to show you, okay? So this is an example that shows you that why a single metric is not a good idea, okay? So you start from your table, confusion matrix, and so as a side, just by looking at these numbers, you can derive the number of elements you have in each class. So basically, if you look at this column here, so if you add these two numbers, 70 plus 15, that's 85, you know you have actually 85 of class 0. Okay? So you just have to, you add up these two numbers, you know the number of elements you have in that class. And the same, if you add 70 plus 5, you have the number of elements that have been predicted as 0. Okay, so you sum along the columns is the number of actual elements in your class, and number summation along the rows is the number of observations you predict as being of a certain class. So here you can compute a number of things, and we're first going to compute the recall. Okay, and so the recall is the ratio of the proportion of positive that are labeled as true positive. So that's true positive divided by all the numbers that should have been positives. So that's the true positive and the false negatives. So that's true positive is 10, and then true positive is 10, and false negative is 5. Okay, so you have something like 67% recall. Okay, so remember, so it means like you will flag correct 67% of the positive as indeed being positive. Okay, so if you look at all the class 1, you will label 60% of that class as correctly, right? And the accuracy in this case is the number of correct classifications, so 70 plus 10 divided by the number of observation, which here is conveniently 100. Okay, so you have 80% accuracy. So that number tells you that 80% of the time, 80% of your predictions, if you want, will be correct. Okay, so if you look at your entire test set, 80% of the predictions will be correct. Okay, so this is all fine, but I'll show you that I can beat any of these two numbers with very trivial classifiers. Okay, so the first classifier always returns 1. Okay, so it's not a very smart, it's very non-informational. Okay, you really don't learn anything, you just return 1 all the time. So let's see what happens. So we know that the actual number of 1s, so if you come back here, so the number of 1s we have in the data set is 15, and the number of negatives is 85. Okay, so we have more negatives than positives. So we know that this sums up to 15, sorry. And in this case, because we always return 1, we know that if indeed the class is 1, then will be good all the time. Okay, so 100% of our predictions when the object is of class 1 will be indeed correct. Okay, so there is no false negative because we don't produce any negative number. Like there is no zeros. We never produce 0. Okay, and of course the drawback of that is that you create a lot of false positives. Okay, so there is a lot of times where you should have the output should have been 1, but we just 0, but we just output 1. Okay, so you have 85. All the elements of the negative class are falsely reported as being positive. So fine. So this is your confusion matrix. And when you look at the recall, so the recall is the number of true positive divided by true positive plus false negative. Okay. So we see that true positive is 15 and false negative is 0. So we have 15 divided by 15, it's 100%. Okay? So it's amazing. You have a system that will retrieve really 100% of your positive class. Okay? So you can't fail. But it's a bit like asking, if you ask for a search engine, the analogy would be if you type Google for a link, for keyword, and Google returns you all the possible links that he has in his data set. Okay, that's kind of a bit the analogy. Okay, you're sure you cannot miss because you'll have all the links back to you. Okay, so or it's the analogy is like if you do you had drug for cancer and you always say that the person has cancer, then you're sure that if a person indeed has cancer, you will tell that the person has cancer. Okay, you can't make a mistake there. But obviously, it's not very interesting. But still, the recall is 100%, which is the highest for that metric. You can do the same for the accuracy. Okay, the accuracy you'll be thinking, okay, the accuracy is kind of harder to fool. You cannot come up with a crazy classifier that would beat any other system. But look at what happens if, in this case, we always return 0. Okay, so we have a classifier B, and this time it only returns 0. Okay, so same deal. We can compute the confusion table. And in this time, the true negative is very high, okay, because all the time you return 0, you return negative, so you will get all the negative class. So you're doing very good here. And of course, you have no false positives because there is no positive as an output. And you're doing badly for the false negative, of course, but that's what it does, okay? And when you look at the accuracy, which is the sum of these two cells divided by hundreds, then you see you have 85%, and 85% is higher than what you had in the previous classifier, okay? So even though this classifier is really stupid, okay, you still manage to get a very high accuracy. And the reason why you have a very high accuracy here is because you have quite an imbalance between the two classes. Okay, you have a lot of elements in your test that actually are negative. Okay, so usually happens. Okay, if you have imbalance in data, if in data you have lots more of class 0 than class 1, say, then the matrix will get skewed in that way, okay? Because it's easy to fool the system and get very high number, okay? Anyway, so something to keep in mind. And you can do the same for F1, you can do the same for any of the other metrics, okay? There is not a single metric that will get you, that will be able to distinguish between, clearly between all the classifiers. You always need to, a good classifier has to perform well on at least 2 metrics. Okay, so you need to have at least 2 metrics and to perform well on these 2 metrics to have confidence that it is doing well. Okay, so when we come to, so you've seen this morning something called Roc Curve. So it's called, refers to receiver operating characteristic curve, which is actually something quite old, okay, that dates back from the 50s. And it basically like this, okay? So the idea is that you, if you take a linear classifier, okay, you would have something like, something like that, okay? So you compare your linear combination against some threshold, okay? So this threshold is defined by 0 in our system, but you could imagine you can change that threshold however you want to have it, okay? And basically, the way you change the threshold is a way of making your, if you increase the threshold, it means it'll be harder to produce a class 1, okay? So you're making more conservative decisions. You're trying to say, okay, I really don't want to have a lot of false positives, so I just increase the threshold, so I make sure that when I produce a positive, I'm really sure about what I'm doing, okay? And you can do a whole family of these classifiers, okay? So you can take a lot of values for t, and basically you have different performances. And this is what happens, okay? So if you take a classifier and you report, so I'll just make sure it's, yeah, so here what you have is curves corresponding to a class of classifier, okay, a family of classifiers. So if you take, say, your linear regression or something like that, and you report all the values of, so it's false positive rate and true positive rate for that classifier. So you record two metrics, okay? And you record a number of points, and all these points will be for different values of t. So maybe here, t will be very low, and then t here will be very high, okay? So you go for different values of t, you measure the metrics you have, you measure these two metrics, so the false positive rate and true positive rate. And basically for that classifier, okay, it's just one classifier, one class of classifier, you actually generate a whole bunch of classifiers, and they all fall into a curve, they form a curve, okay? And you say, so instead of saying my classifier does that, you say my family of classifier followed that particular curve. And so what's interesting here is that then instead of comparing just these numbers, you actually compare curves, okay? And you would see that a classifier that does excellent will be kind of around here, okay? So that's this top curve. And the reason for that is it means that the false positive rate here will be very low, okay? So there's not much error. And the true positive rate, which is your how often you correct, is very high, okay? So you want to be in that side of the plots, okay? So you want something that really climbs sharply and then tail off here. The worst you can do is to be like a random classifier, and a random classifier has basically both rates equal. So the number of errors you make versus number of correct decisions you make is roughly the same. Okay, so if you're taking random decisions, then you'll be equally wrong or right, okay? And you'll be somewhere along that straight line here, okay? So if you ever have a classifier, you plot something and you're here, you know that's something wrong, that's not possible, okay? You're doing very bad here because you could just negate whatever your outcome is and do better, okay? So if you're here, that's bad news. All right, so there's one last metric you've seen in the lab. It's called, and it's not in the slide, it's called area under the curve, okay? And basically what it is so if you have your false positive rate here, and you have your true positive rate here, and you have your curve, which is somewhere like this, the area under the curve is well, this part here, indeed the area under the curve of your RSC curve, okay? And the idea here is like, if you have, if you're doing very well and your Roc curve is something like that, then the area is almost 1. Okay, it kind of fills up the entire square. So the surface you take is 1. And if you're doing very poorly here, you'll be at almost 1/2. Okay, so it kind of gives you a one number that allows you to compare two curves if you want. Okay, so the greater the number, the more you're going to be something pushed toward the corner here and be perfect. Okay, so you just want the highest number there. But once again, this is just one number that compares different curves, and it's not the full story of your classifier. Okay, so it's not enough. Right, so this is the kind of terminology you can have. And I just wanted to say that when you move on to multiclass, most of what we've seen for binary just doesn't work anymore, okay? And the reason for it is because when you look at an example here of a confusion table, so you can always do a confusion table, and that's what you should do all the time, okay? It's a very good exercise to do confusion tables because you can pinpoint what's going on in your data. So when you look at this, you see, right, so when we're good, we're on the diagonal. That's still true. But all these elements here are errors, okay? And when we had two classes, we had two types of error, and we get them names, true positive, false negatives. But now we have 6 types of errors, okay? And if you have 20 labels, we're going to have plenty more types of errors. And we're not going to start giving names to all these errors, okay? So kind of all what we've seen before kind of falls apart at that point. But what you can do is what people do, and it's a bit arbitrary, is trying to aggregate all these metrics in some way, okay? So here's 2 ways of doing that. One is called micro-averaging, and the other one macro-averaging, and there's some different schemes of weighting and so on. But the idea here is like you split your problem into 2 classes problem. So you say, am I classifying, you're looking at a particular class K, and you check, am I doing a good job at this class K? So is this class correct, or did it belong to another class? So you just isolate the problem, the K versus the rest of the other classes. And then if you look at that, you can talk about true positives, false negatives, and so on. And so the negative, what positive means like you indeed belong to class K, negative means no, it didn't belong to class K. And so there's 2 ways, and you look into the slides for more detail. It really just differs in the way you do the aggregation. So one, it's called the micro. So you keep the same, all the same formulas you had about true positive and false positive and so on. But what you change is the definition of what is a true positive. So you said true positive is the sum of all my true positive for all the classes. And the false positive is the sum of all the false positives I have. All right, so you just look back and just do the sum of all these guys. So that's the first version. The second version is when you keep the definition of the metrics, so you still, for instance, look at the precision here, it's still true precision, true positive divided by true positive plus false positives. So there's still the same definition for a class K, but what you do is you average over all classes. So you average your metric over all classes, okay? So 2 ways of thinking about it. Either you keep the definition of what your metric is, we just change the definition of what true positive is, or you change the definition, you don't change the definition of your true positive, you still use them the same way, but you change the definition of what the macro, you just average over all these metrics. So just keep in mind they exist, and they will give you different results, of course, okay? So it's easy to find the metric that makes your results more flattering than the opposition, okay? There's always one metric somewhere that will help you. All right, so it comes back to this idea of 3 sets, okay? So we've seen you have different metrics, and it's a bit trickier when it comes to multiclass, but still, you can come up with some numbers. So remember the way it works, okay? So you have your training set, and you're going to train for that, and you're going to get your weights, okay? Your classifier will be ready. Of course, the problem is the problem of overfitting. You're going to do very well on your training set. And that's kind of by definition, like you hope you're going to do very, very well in your training set. The real question is what happens when you try with new, when you go to the real world and you have new examples coming to you. Are you going to do well? Well, probably not, because you're not overfitting there, okay? So this is the idea behind splitting your data into different sets, okay? So you have first the training set, okay? So that's the one you know of. And you have the testing set, which is test set is just a bunch of samples you haven't seen before, and you're going to test on that and see get the metrics. So this is where you use the metrics, okay? You don't use a metric on the training set, you use them on the test set, obviously. But of course, what happens is that, say you're working in a startup in a company, and you're trying to have a release every week or so, and you're trying lots of ideas, and basically you're going to look at the test set, how you perform on the test set, and you're going to do better and better on the test set. But even so, you're not training specifically for the test set. You're kind of selecting for the test set. By that I mean that you're going to only keep the results. You're doing a manual selection. You're only keeping the algorithms that perform well on the test set. So even so, you're not, you don't have a for loop, or you don't put actually the test sets samples in your training set. Somehow, in the process of optimizing for your results in the test set, you're kind of training for it, okay? In a non-efficient way, but you're still training for it. So very quickly, what happens is that you're kind of training for the test set and on the test set. And so your test set, the results you get there, you start to kind of overfit. The results you get are very good on test sets by definition, because you just keep the one that work on it. And therefore, if you give data from the real world, you're going to perform worse, all right? So in a way, your test set is contaminated, okay? So a trade-off is to use another set, which is called dev or validation set. And that's the one you use for the day-to-day optimization, kind of meta optimization, if you want, okay? So you have a bunch of algorithms. You're going to train them on the training set. That's fine. But you're going to compute the metrics on a validation set. It's kind of an intermediate test set, if you want. That's the one you use on day-to-day. And then when you're happy what you found the best parameters for your algorithms on the test set, on the validation set, then you move on, say at the end of the month, on the test set, and you look how well you're doing. All right? So it's kind of the idea, like you use different sets for, and the test set, the last one, ideally you only see it once, okay? You only use it once, okay? In practice you cannot, but that's kind of the idea, okay? So you will have to use 3, and conceptually you could use more than 3, okay? You might have to use more than 3. So it comes down then to how do you go about doing them, okay? So I'd say training set is whatever kind of data you have to work on, okay? Just you go for it, first thing to do, you get a lot of data, so that's your training set. Then you need the test set and validation set, okay? You get that ready, pick up some metrics. Doesn't really matter which one, okay? Take a few, and then as you go along, you might update this metric, change them, and so on. So you train on daily basis on your validation set. So the validation set and test sets are, it used to be the ratio that you had something like 80% of your data on your training set and 20% on your test set. You read these kind of numbers, or 60, 40, and so on. In the lab, you had the random splits. Splits. You could split the data in between training and test, and you had to give a proportion. The point is, really all you want is, so all this percentage breakdown made sense in the times where the test sets were the order of 1,000 or 10,000 samples, okay? But now that you have potentially billions of training set, it's a bit annoying if every time you want to evaluate your metric that you actually have to run on hundreds of millions of points, okay? That'd be very slow. So a few tens of thousands of points for the test sets or dev sets is plenty enough, okay? Just think of what kind of percentage digits, you want to be able to compare. If you want to be able to compare a difference of 0.1 in one of the metrics, maybe you need to have, at least 1,000 or 10,000 points. Okay, so the number of points you have in test set and validation set determines how accurate you are in in your percentages in your metric. So that's kind of the point here. Okay, so these things must be set up even before you have models. Okay, so when you start, okay, you start in a company, they have a problem. This must be set up. The whole workflow must be set up from the onset, even before you start talking about classifier system. Okay, you need to have at least a beginning of something, and this can change. Okay, you can iterate those, but first thing first is you get that set up. Okay, all these three data sets ready. You get some metrics, and then once you have that, you can compare what you're doing. It's much easier to document what's happening. All right. The last point I mentioned about imbalance in data. So it's quite often that you have a data set that has a lot more of one class than the other, and that is a bit of an issue. Okay, and that is because when you look back at the loss function, so the loss function usually what they solve for is something that looks like the accuracy. Okay, they don't look at the two errors in different ways. They just treat it the same way. Okay, an error is an error and doesn't matter. So okay, it's a bold statement here, but most of the loss functions you'll be using are kind of minimizing some kind of something to do with the accuracy. And we've seen it's an issue. Okay, so if the data set has a lot more of class 0 than class 1, then it will say, well, then I'll have to cater for class 0 because it's way more important. The majority is more important. So that might not be true. Okay, detecting cancer, for instance. Okay, maybe the 1% is more important than the 99%. So maybe you want to rebalance that. There's different ways of doing that. One is you resample your data. So you just discard plenty of data and make sure that it's an even balance. Or you apply some weights at a general level, and there are techniques for doing that. I think that's one in the lab, you have that. All right, so to summarize, one single metric is not enough, okay? And funny enough, when you do loss functions, that's just one single metric, okay? So when you're doing training and loss functions and so on, you're just optimizing for one metric, but when in fact we should be optimizing for two, okay? So you need plenty of metrics, get them set up, and you need to have different sets, training sets, validation sets, and test sets, okay? So usually training and test set is not enough when you want to optimize on the data, on the algorithm. When you want to work with different iterations, you need to have at least 3 sets. All right, that's it.